Alright, so we've come up with a way to generate an entry in a specific range at random. So now we can put all the tools together to come up with a quick select for matrices. So in particular, it's going to be almost identical to the traditional quick select. So I'm just going to mention what are the differences. So now, instead of quick select being defined on an array, of course, we're going to have it defined on input, which is our whole matrix, I naught, j naught, I1, j1. So these will take into account exactly the submatrix that we're still considering, which range of elements to consider. It's not exactly the same as saying this. It won't exactly be this, but that's the mental picture you want to have in your mind. It's restricting our search space. And the last thing we're going to need is R, the specific rank we want. So in the end, that's just going to be n squared over 2 because we want to look at medians. So when we actually run this, we'll have m, 1, 1, and then nn, i.e. look at the range that's everything in the matrix, and n squared over 2 will be the median that we're looking for. So this will be what we actually want, but we're making a more general procedure. So this will be the input for the more general procedure. And the first thing we're going to do is, before we computed some sort of pivot and did computations, there's going to be an extra step here. So we're going to have to look at this m, which is exactly the count between. So these are the number of entries that are larger than I naught j naught and smaller than I1 j1. So this is exactly the thing we computed in part A. And specifically, we're going to do this on m, I naught j naught, and I1 j1. So this is exactly the thing from part A. So once we have this m, this is basically all the relevant entries we should consider. And our base case is just, brute force if m is some constant, so let's say 10. So if we have a small number of things left to consider, we can just brute force enumerate them all using the thing from part A, so we could explicitly list all those entries in O of n time, and then we can just check which one's the rth smallest. So this is easy, O of n time. Otherwise, we're going to let row column be chosen uniformly at random, specifically in the range I naught j naught, I1 j1. So now we're using the thing from part B. This allows us to pick a random entry, which is described by its row and column number. So once we have this, we can create a pivot element just as we would before. So this is our random pivot. And now we want to essentially do the partition procedure. And the way we're going to do this is we're going to define our pivot P, and we're specifically going to look at its rank. So let's say RP, and we're going to do count between again. But this time, we're doing it between I naught j naught and RC. So the entry we picked at random is partitioning the set of possible entries we should consider. So we're going to look at everything that's smaller than this pivot, essentially. So very similar to partition and quick select from class. And we're also going to need a +1, just because we're going to include our queue itself. Then we'll do the same thing as in quick select, where we just continually try this. So if RP is less than m/4, or RP is greater than 3m/4, then we're going to repeat the process. So we're going to keep doing this until we find a good pivot. And then finally, we do the normal quick select stuff, where we just check, is the rank we were looking for exactly this rank? If it's so, we return MRC. This is the element we want. Otherwise, if R is less than RP, we're going to recurse on I0 J0, and the upper bound's now RC. We're still looking for rank R. Otherwise, we recurse. Now RC is going to be the lower bound, and we go up to I1 J1, and the new rank we're looking for is R minus the pivot rank. So if you have questions of why we're doing this, look at quick select, the normal version. But otherwise, these are just a slight modification to make this work for general matrices. So that gives us in total the whole algorithm. That's all we really need. And of course, this is randomized. So the analysis is going to be very similar to before. And mimicking that analysis, we'll get O of n log n. And the key factor here is that we can compute essentially the pivot procedure. So this is kind of like pivot. We can do that in O of n, and we can generate efficiently by parts A and B. So that's what allows us to get this savings in time. And that's everything. So check out the original quick select algorithm if you want to see more of where these ideas come from, and this is how you can tweak them to make it work for a more general problem.